Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi and today we are going to discuss about the module Spectral Classification and in that Saha's ionization formula from the paper Astronomy and Astrophysics. After studying this module, you should be able to understand that Saha's considered ionization process as akin to chemical reactions. After studying this module, you will be able to learn to derive Saha's ionization formula. We will be able to explain that the degree of ionization of a given species of atoms depends mainly on temperature. Then we'll appreciate that the electron pressure plays a crucial role in distinguishing stars within a spectral class. We'll be able to derive the ratio of excited hydrogen atoms to the total number of hydrogen atoms. After this module, you'll be able to explain why Balmer series are strongest in spectral class A, that is, with the temperature approximately equals to 10,000 Kelvin. You'll be able to compute the ratios of singly ionized helium and doubly ionized helium to the total number of helium atoms. You will appreciate that why helium lines of helium-2 are strong in spectral classes O and early B. After studying this module, you will be able to calculate the ratios of neutral, singly ionized and doubly ionized calcium atoms to the total number of calcium atoms. We will appreciate the reason for calcium-2 lines being intense in the temperature range 4000 to 7500 Kelvin and being present at the temperature as high as 14,000 Kelvin. So before getting into the details, let us have a brief intro. In the previous module, we discussed the variety in stellar spectra. We found that the Howard scheme of stellar classification cannot accommodate all this variety. Therefore, classes Q, P and Wolf-Rayet has to be introduced at the top of the classification and classes R and N were introduced at the bottom of the classification scheme. We also learnt of some of the prefixes and suffixes used along with the spectral class to fully describe the peculiarities of the stellar spectrum. As prelude to the derivation of Saha's ionization formula, we derived Boltzmann law governing the population of excited atomic states. We stopped short of deriving the Saha formula, which we take up in this module. Saha's ionization formula. Let's recall that the chemical reaction can be written as summation over I, Ai into epsilon I equal to 0, where I are the reactants and A are the integers, sometimes referred to as a stoichiometric coefficients. As an example, consider the simple reaction 2 into H to the subscript 2, that is twice of H2, plus O2 equals to 2H2O. Here, 2 molecules of hydrogen and 1 molecule of oxygen combine to give 2 molecules of water. Note that the coefficients of H2, O2 and H2O are all integers. The above equation follows from the law of conservation of mass, which states that the total mass of reactants must be equal to the total mass of the products. The law was discovered by Lavoisier. Actually, there may be a slight change in the mass during a chemical reaction. However, Lavoisier's time, there were no means to detect these slight changes. The law of conservation of mass led to the understanding that the quantities of reactants and products are always in the ratio of simple integers. The law of conservation of mass and the laws of definite proportions and multiple proportions led to the formation of atomic theory of matter. For equilibrium at constant temperature and volume, and for given quantities of the various reactants, the condition of chemical equilibrium reduces to summation over I mu I epsilon I equal to 0, where mu I is the chemical potential of the reactant. Now, what is a chemical reaction and the chemical potential? Chemical reaction is an equation in which the products or the reactants, they react together and they give some output, which is output integers, which are the products. Chemical potential is the thermodynamical variable. It is basically Gibbs free energy per molecule. It turns out that above equation is an essential condition for chemical equilibrium. If we use the relation as we stated that in the previous module, eta equals to mu divided by K into T, where mu is the chemical potential, T is the temperature, K is the Boltzmann constant, then this relation reduces further to summation over I eta I into epsilon I equals to 0. Suppose now, following Saha, that the process of ionization of N times ionized can be considered a chemical reaction written symbolically as x to the subscript r equals to x to the subscript r plus 1 plus e. Then the above two equations gives us eta r equal to eta r plus 1 plus eta e. If the particles are non-relativistic, then the energies of the particles are given by E equals to P square divided by 2 into ME. Then E r comma I can be written as it is equal to P square divided by 2 into MR plus xi Ri. Then we can also write E r plus 1 comma j equals to P square divided by 2m r plus 1 plus xi r plus 1 comma j plus IR. Here the ionization potential, that is from the ground state of the R times ionized atom, etas are the excitation potentials and the masses obey the relation. The masses obey the relation mr equals to m r plus 1 plus me. Notice that we have assumed the same momentum for all the particles. This does not matter because ultimately we are going to integrate over all momenta. This is because we are interested in the relative numbers of the three types of particles of all kinetic energies. Now, using the above equation in the expression for the particles per unit volume in the momentum range, or that we have discussed in previous module, that is dnp equals to g into 4 pi p square dp divided by h cube into e raised to the power eta into e raised to the power minus p square divided by 2 mkt. If we integrate over the entire momenta, we get for r times and r plus 1 times ionized particles per unit volume. So nr will be equals to br into t, that is br is a function of t, e raised to the power eta r multiplied by 2 pi m eta kt divided by h square to the power 3 by 2. And similarly, we can get the expression for nr plus 1. Now dividing these above two equations and then multiplying by ne, we can get nr plus 1 into ne divided by nr equals to ne into e raised to the power minus eta e b r plus 1t divided by brt into mr plus 1 divided by mr to the power 3 by 2 into e raised to the power minus ir by kt. This equation is called as Saha's ionization formula. The quality of this formula is Saha's formula in the form derived above holds even when the electrons are degenerate. Saha's equation and stellar classification. For the purpose of illustrating the application of Saha's equation to the spectral classification, it will suffice to assume uniformly that dynes per centimeter square. It may be pointed out, though, that although the overall nature of spectrum is determined by the temperature, the details of the spectrum are affected a great deal by the pressure. In fact, it is a finer detail that enables us to distinguish the various types of stars within the same spectral class. Hydrogen ionization. Saha's ionization formula shows that hydrogen is very quickly ionized as its temperature increases. However, to get the strength of Balmer lines, we must know how many hydrogen atoms are excited to the level n is equal to 2. We can see the given figure below, which describes that at around 5000 Kelvin, hydrogen is completely unionized, and by about 15,000 Kelvin, it is fully ionized. The partition functions of the neutral and ionized hydrogen atoms are very different, and we can have the data of the fraction of ionized hydrogen atoms at various temperatures at PE equal to or pressure equal to 100 dynes per centimeter square. The data of the fraction of ionized hydrogen atoms at various temperatures is plotted in the given figure, and we notice that from completely unionized state at about 5000 Kelvin, hydrogen becomes almost fully ionized much before the temperature reaches 15,000 Kelvin. However, the degree of ionization by itself is not very important. To get the strength of hydrogen lines in the visible region of the spectrum, we must get the ratio of the excited hydrogen atoms to the total number of hydrogen atoms, because if the atom is not in an appropriate excited state, it will not be able to absorb radiation corresponding to the Balmer and other series. Fraction of excited hydrogen atoms. To find the fraction of hydrogen atoms which are excited to level n is equal to 2, we have to combine Boltzmann formula for the distribution of excited states in an atom with the Saha's ionization formula. The results of computation show that the number of such atoms is maximum around temperature of 10,080 Kelvin. Therefore, the strongest line of hydrogen is expected in class A. The given figure shows the variation in the fraction of atoms in the state n equal to 2 with temperature. It is easy to see that the Balmer lines will reach their maximum strength at around temperature of 10,000 Kelvin or in the spectral class A. So we see clearly the role of temperature as the basis of spectral stellar classification. So this figure is the excitation of hydrogen to state n equal to 2 is maximum at temperature around 10,000 Kelvin, and the strength of the Balmer lines is therefore maximum in spectral class A. The topic is helium lines. Computation using Saha's ionization formula shows that neutral helium lines are expected to be strong in the temperature range 12,000 to 14,000 Kelvin. Singly ionized helium lines are strongest in the temperature range 16,000 to 30,000 Kelvin. The figure given here shows the occurrence of helium-1, helium-2, helium-3 as the function of temperature. Helium lines. The above graph shows that singly ionized helium, helium-2 lines dominate in the range 16,000 to 28,000 Kelvin, and O5 star shows ionized helium line in its spectrum. So the given figure here is the sketch of spectra as in Kaufman-Williams book. The original data are attributed to J. Jacoy and D. Hunter and C. Christian. The graph of the fraction of ionized helium atoms shows that neutral helium, helium-1 lines appear in the range 12,000 to 14,000 Kelvin. The spectrum of stars of spectral classes B1 and B6 show neutral helium line in their spectra. The figure given here are the sketches of spectra again in Kaufman and Williams book, and the original data is again attributed to Jacobi, Hunter and Christian. Calcium lines. Calculations based on Saha's ionization formula show that unionized calcium lines will be strong in the temperature range 3000 to 6000 Kelvin. Singly ionized calcium lines dominate in stars which have surface temperature in the range 4000 to 10,000 Kelvin. The lines of calcium 2 are in the ultraviolet region of the EM spectrum. So, the given figure here shows the calcium 1, calcium 2, calcium 3 lines, or we can say that the given figure shows the fractions of ionized calcium atoms as a function of temperature. Although the lines of calcium 2 are very intense in the temperature range 4000 to 7500 Kelvin, they are present even at the temperature of 4000 Kelvin, and calcium 3 lines are in the ultraviolet region. The graph given below shows that the lines of neutral calcium will be strong in the temperature range 4000 to 8000 Kelvin. This portion of the solar spectrum, that is temperature in the solar spectrum is almost equal to 6000 Kelvin, shows the lines of neutral calcium. This tiny portion of the solar spectrum in the given graph tells us iron, calcium and lithium are all present in the solar atmosphere. Here the graph given shows the lines of neutral and ionized helium in spectra of stars of classes O and B. Here the given figure shows the spectra of stars of various spectral classes show lines of hydrogen and ionized calcium among others. So students, let us summarize what we have learnt in this module. First of all, we saw that Saha considered ionization process to be like a chemical process. Secondly, we realized that Saha's ionization formula holds for degenerate as well as non-degenerate electrons. The primary influence on the degree of ionization is the temperature. The next, we saw that the slight modification in the spectra introduced by pressure plays an important role in classifying stars based on their luminosity. The degree of ionization of hydrogen by itself is not very important for determining the strength of hydrogen lines in the stellar spectra. The next, we learnt that to get the strength of hydrogen lines in the visible region of the spectrum, we must get the ratio of the excited hydrogen atoms in an appropriate state to the total number of hydrogen atoms. The Balmer lines of hydrogen reach their maximum strength around a temperature of 10,000 Kelvin or in the spectral class A. So we learnt that the Balmer lines of hydrogen are in the spectral class A with their maximum strength of around temperature 10,000 Kelvin. Then we learnt and dealt with the calculations based on ionization formula showing that helium second lines or helium 2 lines will dominate in spectral classes O and early B, while helium 1 lines will dominate in later class B. Then we saw that calcium 2 lines may be present at temperatures as high as 14,000 Kelvin, but they are particularly intense in the temperature range 4000 to 7500 Kelvin. Calcium 3 exists at temperature above 14,000 Kelvin, but its lines are in the ultraviolet region of the electromagnetic spectrum. Thank you.